300 feet beneath the English Channel, 31 miles long, the longest underwater train tunnel in the world, a link between a country and a continent. Now, the Channel on Modern Marvels. Modern Marvels. It used to be that the only practical way to get from England's famed White Cliffs of Dover across the English Channel to the French coast was by boat. The trip across the temperamental currents of the Channel could be unpredictable and unpleasant. Now, crossing the Channel is a 35-minute snap, a simple matter of shooting by train through the longest underwater tunnel in the world at speeds of up to 100 miles an hour. Passenger trains can now speed from Paris to London in 3 hours. Shuttles carry trucks and cars which drive aboard remarkable open-ended wagons and line up bumper to bumper.
It's quite a pleasant experience, actually. It's much nicer than travelling on a boat or the Sea Cat or anything else, because it's not so choppy. Weather's guaranteed down under the tunnel, so it's quite nice.
The Channel Tunnel, otherwise known as the Channel. It's not much to look at, this long, narrow corridor in the ground, but make no mistake about it. The Channel Tunnel is one of the engineering marvels of our time. It took an army of some 7,000 workers 7 years and almost $14 billion to drill this 31-mile link between England and France. They had to drill not one but 3 underwater tunnels in the harshest of environments, fighting bad rock, unexpected fissures and serious leaks, while tracking a rumpled path of bedrock that dips 150 feet beneath the Channel floor.
To drive a tunnel 30 miles through chalk and to then fit it out as a railway system, to build 2 very large road-rail interchanges at each end, and to complete the project was an achievement. It really is another wonder of the world that it was done at all.
The tunneling team also had to overcome a cultural divide between England and France and a deep hostility to the very idea of linking the 2 lands.
Here we were connecting 2 countries that hadn't been connected for 8,000 years. It was a huge advance in imagination, in technique, and in sheer persistence to get it done.
Well, the site workers used to say this is, the biggest thing since the pyramid sort of thing, I mean, it is, as an engineering feat, it's absolutely phenomenal.
Before the Channel opened in 1994, most people had to cross the English Channel, which averages 23 gale force storms a year, by boat. The often stormy passage was one of the most heavily trafficked waterways in the world, with as many as 750 ships a day carrying people and freight between Britain and France. The dream of an alternative means of making the trip goes back at least as far as 1785, when a pioneering aviator flew over the Channel in a hot air balloon. It was a Frenchman named Albert Mathieu who in 1802 drew up the first serious plan for a Channel tunnel, envisioning a horse and buggy passageway to be ventilated with a chimney-like shaft drawing air from above the waterline. The proposal was as bold as it was impractical. England and France were at war, and the idea of giving Napoleon direct access to the English mainland was not very popular, at least not among the British. Another Frenchman, Thomas de Gaumond, was the next champion of the Channel Tunnel idea. De Gaumond proposed building an artificial island in the middle of the Channel and linking it to each coast with prefabricated tube tunnels that would lay on the Channel floor. To allay British fears, he included flood valves in his design that could inundate French troops in case of an attack. Other 19th century schemes for a cross-channel link included one for a kind of submarine on wheels, and another for an underwater tube suspended by a long line of floating anchors. The invention of the tunnel boring machine, or TBM, in 1875 brought new life to the Channel Tunnel idea. This massive air-powered drill was, in its essentials, identical to the TBMs in use today, with a rotating drill head that could gnaw through the toughest geology at the then phenomenal speed of an inch a minute. In 1881, pioneering TBMs actually began drilling off the coast at Dover and on the French side at Calais.
This 1881 tunnel was driven in the same chalk marl that we chose in 1985. The geologists knew that this was the best stratum. What they couldn't be sure of at that time was whether it went all the way across to France. I don't think they actually developed the notion of how you would get this tunnel all the way across. I think government said, prove to us that you can bore a tunnel in this material and that you know where to bore it. And that they did. And the tunnel is, what, about 7 feet in diameter. You can walk down it, and we did walk down it. And this rotary machine cut a beautiful, smooth, circular bore in the chalk. So it demonstrated it could be done.
After a year of drilling, each TBM had burrowed more than 5,000 feet. But as the tunnel became more of a reality, English invasion fears returned. And the government pulled the plug on the project because officials said it would fatally weaken Britain's national defense. Support for a channel tunnel persisted in the new century, and the British government finally commissioned borings of the channel floor in the 1950s to see if tunneling was geologically sound. As luck would have it, a layer of rock called chalk marl, ideal for tunneling because it was easy to cut, strong and impermeable, ran the breadth of the channel from Dover to Calais. Unfortunately, the chalk marl was sandwiched between unstable layers of rock and clay that could collapse if disturbed and trigger a flood. Worse still, the path of the chalk was narrow and furrowed and would be extremely difficult to follow. Nevertheless, engineers were confident that they could follow the chalk marl, and in 1974, TBMs once again began to chew their way toward each other from either coast. And once again, the British backed out, ostensibly because government funding fell through, but also because the idea of connecting England to Europe was still highly controversial.
The Brits, I suppose, we're an island race, and for generations we have felt safe from invasion because of this narrow strip of water. It doesn't make any sense in today's terms, but it stopped the Romans for a long while, and it actually kept Hitler on the right side of the water. I can remember in the days when I was trying to sell this idea to the public in 1985, having old ladies wave umbrellas at me from the front row saying, "You rascal, you know, we don't want to be connected to the French. There's a danger."
The idea of a channel tunnel seemed dead in the water, so to speak, until it was revived unexpectedly in the 1980s by the unlikeliest of partners. England's conservative Prime Minister Margaret Thatcher and socialist French President Francois Mitterrand. Neither wanted to risk government funds on the project, but both were willing to allow banks and other investors to foot the bill and take the risk.
It's really quite remarkable that these two particular leaders should have decided to get the act together and do it. But I think they each saw a wider political advantage to having their name upon this scheme. They knew that it could be done.
A handful of attention-getting designs quickly came to the fore, including one for an outrageously long 21-mile suspension bridge, more than a dozen times the length of the Golden Gate. And this hybrid plan that combined two artificial islands, two tunnels, and two bridges. The winning proposal for a rail-only link called Eurotunnel was reassuringly straightforward. It consisted of 3 tunnels, 2 of them 23 feet in diameter for trains coming to and from France, and a smaller service tunnel in the middle for maintenance and emergencies. The tunnels would stretch 31 miles from terminal to terminal, 23 miles of which would be underwater. The most daunting aspect of the proposal was the sheer amount of tunneling involved, 125 miles worth in all. In addition to the 3 main tunnels, large crossover chambers in which trains could change direction would have to be cleared. Cross passages linking the 3 tunnels every 1,200 feet and enabling people to escape in an emergency were also part of the plan. As were scores of piston relief ducts, smaller overhead connecting tunnels that had to be drilled every 800 feet to allow the pressurized air created by speeding trains to escape. The plan called for the tunnel to be built by a consortium of 10 major French and British engineering construction companies over a period of 7 years at a cost of almost $7 billion. Over 200 banks would put up the money, making this the most expensive privately funded construction project of all time. The budget, of course, was more or less a guess. No one had ever built a tunnel like this before, and it would double almost to $14 billion by the time the tunnel was finished in 1994. A large chunk of that budget would be spent building a dozen 800-foot-long boring machines, mechanical molds that could chew their way through mile after mile of channel floor. The Babylonians built the first underwater tunnel under the Euphrates River in 2180 BC. The British built the second 4,000 years later under the Thames in 1843. The channel will return on Modern Marvels.
AM, watch a lot.
Turn to the channel on Modern Marvels. The first big question facing the French and the British as they prepared to drill 3 tunnels across the English Channel was the question of access. How to get people and supplies in and out of the underwater construction site. The British decided to drill 2 slanted passageways or adits descending from the base of Shakespeare Cliff, some 200 feet to the starting point of the tunnels. In addition, they dug out 3 large shafts through which they could lower heavy equipment like the tunnel boring machines. The French, on the other hand, took a more dramatic approach, digging out a spectacular trench called Le Puits de Sangotte, the Well of Sangotte. 195 feet deep and 165 feet wide, Sangotte was large enough to swallow the Arc de Triomphe of Paris.
In a shaft of that size, all 3 tunnels could pass through the bottom of the shaft, which meant that you had vertical access to all 3 tunnels, and you could draw the material straight up out of them. And if any one of them got blocked, it didn't affect the others.
The French TBMs were lowered piece by piece into the Sangotte well and then assembled over a period of months in roomy starter tunnels that led to the smaller tunnels to be drilled by the TBMs. By early 1988, TBMs on both sides of the channel had begun drilling the service tunnel, the first of 3 passages that would make up the channel complex. Over the next few months, 4 more TBMs would set to work grinding away towards each other and excavating the 2 larger tunnels through which trains would eventually run. In terms of size, power, and speed, tunnel boring machines had come a long way since their invention in 1875. These 1,400-ton behemoths boasted revolving cutter heads that stretched out as much as 28 feet in diameter, dwarfing the men who worked the machine. Rotating at 3.5 revolutions per minute, the blades studded with clusters of steel teeth would grind through the hardest rock at 15 feet an hour.
To actually stand at the face of one of these things is massively impressive. You're talking sort of 7 meters across with all these little cups, and you think, how on earth is this going to dig through the ground? But of course it does, because it just literally eats it away as it goes.
Interestingly, the British and the French did not use the same kind of TBM. The difference was not ideology, but geology. 6 fault lines crisscrossed the first few miles of the French coastline, and that meant that any drilling would be inundated with water from the channel, pouring through the cracks in the earth, making work difficult and messy, if not impossible. During the aborted 1974 tunneling attempt, that's exactly what happened, and the French were determined to improve conditions this time around. It took 18 months to design and build a special waterproof TBM, a virtual tunneling submarine that could plow through the seabed in monsoon-like conditions, keeping equipment and crew bone dry, and that could withstand tremendous water pressure, up to 7,500 tons worth, the kind of pressure the TBM would encounter if water from the channel crashed full force into its path. The British, on the other hand, didn't expect a lot of wetness, so they drilled with more conventional open-face machines. It was a decision they would come to second guess, as unanticipated waterfalls made much of their drilling a very messy affair. The TBM, of course, was at the heart of the tunneling process, eating its way through tons of rock, while carefully following the skinny, wrinkled path of chalk marl across the channel. Surveyors had fixed the difficult route, boring thousands of samples from the channel floor and mapping the seabed with sophisticated sounding techniques. A TBM driver sitting just behind the cutting head kept the machine on course with the help of satellite input and laser probes.
He has at his console a readout of precisely where his machine is with respect to where it ought to be, and so he can steer it to keep it online. It's, if you like, entirely blind flying because you can't see through solid rock, but the machine computer tells him precisely where his machine is with respect to where it should be at any time.
Behind the control room, the long body of the boring machine is busily engaged in two critical tasks: getting the spoil out of the system and installing concrete lining rings to stabilize the freshly drilled hole.
It's a massively impressive tool. The frightening environment, I remember distinctly the first time I went into a tunnel boring machine working. You had to go onto a very, very tight walkway with a conveyor going above you with all the spoil coming from the face. And you'd walk up through all this complex machinery that was lifting segments of concrete, these huge segment linings, nine tons each. And you had to literally creep through these tight, compact areas of the head of the tunnel boring machine to get into the little bit at the front end which actually was doing the work. All the rest of it was mechanically driven, but right at the front, just behind the head, were the guys who were actually putting the linings up onto the wall of the tunnel.
It would take about 20 minutes to erect a complete ring of lining behind the tunnel boring machine. So, provided you could excavate that 1.5 meter ring width in the same 20 minutes, the machine never had to stop.
One of the most impressive things about the TBMs was their sheer length. It took minutes to walk to the rear of these 800-foot-long machines, a distance of nearly 3 football fields. As many as 17 wagons loaded with support apparatus stretched behind the cutting head, containing everything from transformers to grouting mechanisms to ventilation and air compression systems to a lunchroom and an infirmary. The British alone produced and installed over 500,000 lining rings. The concrete used for the rings would support 150 feet of seabed and 150 feet of ocean had to be the strongest ever mixed, twice as strong as that used to line a nuclear reactor. All the granite for the concrete was quarried from a single mountain on the west coast of Scotland to ensure it was of uniform quality. 8 assembly lines churned out hundreds of different types of segments, including concrete rings that were 12 feet thick, used to prop up weaker passages. Spoil disposal was another huge and vital part of the tunneling process. Because their spoil was wet to begin with, the French mixed it with water to create a kind of slurry which they pumped a mile outside of Senghor and dumped atop an artificially created 125-acre basin called Fond Pignon. 6 pumps, each one strong enough to dump enough spoil per hour to fill a baseball diamond to a depth of 36 feet, spewed the slurry to the dump site. The British expected their spoil to be dry, so they opted to haul it out by conveyor belt and train. But once outside of the tunnel, the Brits weren't quite sure how to dispose of it.
Various different options were looked at, some of them requiring train loads of wet chalk to be taken around the country and lost somewhere. There were various environmental concerns about where we were going to dump this spoil. The logistics of moving it away quickly were very important, and in the end it was decided that we would leave it as close to the hole where it came out of the ground as possible.
After looking at 90 possible dump sites, authorities opted to toss the spoil into the channel, adjacent to Shakespeare Cliff, the point at which it had been removed. This proved to be an immense undertaking. To keep the spoil intact so that it would solidify, a huge seawall was built and driven into the sea. The seawall frame was the largest sheet steel structure ever fabricated. As the 5 million tons of spoil rose up through the sea, it congealed and eventually added 73 acres of landmass to England. While spoil teams tossed tons of rock into the channel, TBM teams desperately fought to keep the channel out of the tunnel. But leaks and the possibility of catastrophic flooding would soon become a major concern. 11 men, 9 British, 2 French, lost their lives building the channel. The channel will return on Modern Marvels. The biggest danger in drilling an underwater tunnel is the ever-present possibility of hitting a fissure and triggering a flood. This was especially worrisome in the channel because the tunneling team had to follow a thin, crooked path of chalk marl that was surrounded by weak rock. Hitting bad ground could create cracks in the seabed and bring water pouring down. The thousands of boreholes that had been drilled to study the channel floor posed an even greater danger.
Although you always specify that that borehole gets filled with concrete afterwards, contractors have a nasty habit of forgetting to put the cement in. And so you get a borehole full of stones. And you don't want, in an underwater tunnel, to intersect a hole full of stones that the water can rush down. So all we had to do before we started was to try to determine precisely where over 3,000 boreholes over 200 years had been sunk into the bed of the channel, so as to avoid them with our boring machine. And because we didn't know with great precision where they were, instead of saying each hole is 6 inches in diameter, we said each hole is 30 feet in diameter. Miss it.
The many borings, at least, gave engineers a pretty good idea of what they would find in the channel seabed, or so they thought.
Must have been one of the most surveyed bits of ground in the world, and yet the tunnel boring machine on the UK side still hit unexpected wet ground just off the coast. Everyone expected it to be them to be going through dry chalk all the way, and they had machines designed for that. And so when they suddenly hit wet ground, they were in a bit of trouble.
A bit of trouble is a bit of an understatement. Water began seeping into the British end of the service tunnel in March 1988 as the TBM gnawed its way forward just off the coast. The TBM was designed for a dry environment, but now, week after week and month after month, water was raining into the construction site. Salt water, indicating that it came directly from the sea.
I went into the face at the messiest point, under the UK land drive. And if you can imagine a very, very heavy rainstorm that you're working in constantly at the face, that's what it's like, a very torrential rainstorm, all shift long, the whole time. The main concern was obviously that the ground was so soft that it would literally come in above you, that it would collapse. And therefore, the engineers had to be absolutely sure that they could proceed safely. So the choice was, do you try and turn offline? Do you carry on and hope the ground would improve? Or do you stop and find some other way of digging through it? And in fact, in the end, they made the decision to carry on slowly and as safely as possible in those conditions. But at that time, you were literally moving at a tenth of the speed that you would do normally. So it was very, very, very slow.
The leaks, as it turned out, were coming straight from the channel, through very fine fissures that earlier tests had not picked up. The good news was the cracks were stable, and while conditions were difficult and unpleasant, they were not life-threatening. Nevertheless, the constant leaks cost the crew a year. Later, in dry ground, the TBMs made up the time by drilling at the record pace of 1,200 feet a week. Drilling through the channel bed was the glamorous part of the tunneling process, but supply logistics was a major, if more mundane, challenge. A construction railway, the third busiest rail system in all of England, carried thousands of workers, hundreds of thousands of lining rings, and millions of tons of spoil in and out of the various passageways.
The construction railway at its peak was 1,200 pieces of rolling stock, of which something like about 140 locomotives and the rest were supply vehicles. And we were busier than Heathrow Airport in terms of movements. And every single train went in fully loaded and came out bringing out goods and materials that had to be taken to the surface and disposed of.
All told, the underground supply trains logged enough miles to go to the moon 5 times. Incredibly, the tracking system used to monitor the incessant traffic was nothing more than a magnetic board covered with colored magnets. A more high-tech computerized system would not have been as reliable in this wet underworld.
It was an unbelievable headache. You had all the different tunnels with all the different segments. Each segment had to be numbered and supplied exactly to the number that was going into the tunnel. You had what we called bullets of concrete, which had a lifespan of 5 or 6 hours maximum. So they had to go down. If they were delayed, they went solid, and then they had to be dug out of the bullets, literally by hand.
Interestingly, because of the congestion and long waits, and in order to keep down emissions in the tunnel, many of the workers rode to their job sites on mountain bikes.
A lot of colleagues used to say that it was good fun going in on the bike, especially if you needed to keep fit. Because some of these guys were going up to 27K on a bicycle to the midpoint of the tunnel. The first 9 or 10K is downhill, and then it's very gentle from there onwards. It was only coming home was the difficult part. Up the hill, that was a difficult one.
Even more difficult, making sure that the 2 TBMs eating their way towards each other under 31 miles of channel floor would meet in the middle. After 2.5 years of non-stop tunneling, the time had come for an underwater breakthrough. A British workforce of 3,587 lived in barracks at the job site, put in 10-hour shifts, and earned between $1,000 and $3,500 a week digging out the Channel Tunnel. The Channel will return on Modern Marvels. A return to the Channel on Modern Marvels. One of the biggest questions hanging over the channel tunneling process was whether the tunnel boring machines worming their way towards each other from each coast over a period of years would really meet in the middle of the channel as planned. The TBMs could be off target by as much as 2 feet and still have room to swerve towards each other and hook up. But anything more, a deviation of a yard over a distance of 31 miles, would be ruinous. Tunnelers used lasers and geo-positioning satellites to steer the TBMs. They also turned to micropaleontologists who analyzed tiny fossils in the soil to make sure they were on course.
Chalk was laid down millions of years ago in a big freshwater lake with thousands and thousands of tiny little shell creatures crushed by the weight of material on the top and forming chalk. So in order to ensure that we knew exactly which piece of chalk we were in, we had micropaleontologists employed who would take away a sample of the clay, put it under the microscope, and recognize these microscopic little shells. And if they didn't see the ones we expected, they would say, "You're in the wrong stuff, chaps. You'd better alter the level of your tunnel until you find this correct stratum." So we were constantly drilling ahead of our machine and taking samples.
On October 30th, 1990, after 2.5 years of continuous drilling, the French TBM had eaten its way through 41,612 meters of the service tunnel and was poised to break through on the British side. For the Eurotunnel team, this was the moment of truth.
However blasé engineers like myself may appear, of course, it's a bit nerve-wracking because until you actually join, you can't be sure how precise you are. In order to finally align the tunnels, a small hand-excavated tunnel was driven from one tunnel to the other, through which we could, as we say, close the traverse of the survey and tell ourselves precisely what the junction error was. It was very interesting when you consider that we'd driven a tunnel 22 kilometres out from England, 16 kilometres from France, and they had to meet in the middle, and the distance measurement between England and France was accurate to just about 75 millimetres, 3 inches. The alignment measurement was accurate to 250 millimetres, so we were pretty close.
They're through! They're through! They're through! Hey! There's the handshake we've all been waiting for, Mr. Fagg and Mr.
Amid
Crozet.
cheers, British TBM operator Graham Fagg walked through the opening and on to French soil. French tunneler Philippe Cozet crossed over into Britain. The two had their passports stamped and enjoyed the moment.
Ladies and gentlemen, just about 4 hours ago, for the very first time since the end of the Ice Age, it became possible for the people of Britain to walk to France and for the people of France to walk to the United Kingdom.
Differences between French and British culture, however, surfaced immediately.
And when the tunnel junctioned, of course, there was great excitement. Nobody had walked from England to France for 8,000 years, probably. So when the hole was broken through, we rushed through into the French side, where there were 2 tables laden with Jeroboams of champagne, and a lot of them were ready poured into flutes for us to drink, which we did. The French, of course, rushed into the English side, where there were similar 2 tables laden with plastic cups and mineral water. And the Entente Cordiale nearly collapsed at that point.
Similar celebrations would quickly follow, marking breakthroughs for the 2 other tunnels, the larger passageways on either side through which trains would eventually run. By 1991, the first and riskiest phase of the Channel project was complete. Tunnels under the English Channel were at last a reality. The stage was set for a new excavation challenge, digging out enormous crossover chambers, which had to be big enough to allow kilometer-long trains to cross over and change direction from one tunnel to the next. The crossovers, one on each end of the 3 central tunnels, were the largest underwater chambers ever attempted.
They were excavated first one side, then the other, and then they ate away at the center section. When you went in there during the construction phase, it was awesome, watching them bit by bit, piece by piece, section by section, line the walls, put the tracks in, put the floor down, put the doors in, and all of it had to be taken in bit by bit and constructed in situ. It's absolutely fantastic, but they just did it like piecing a giant jigsaw together in this massive cavern.
The caverns were too large for the TBM teams to quickly install concrete lining rings as they had done in the tunnels. Instead, they used a temporary support technique called shotcreting, spraying a layer of concrete onto the high ceilings and walls to keep them from crumbling.
Shotcrete is a thin skin of sprayed concrete to spray directly onto the rock. It creates, if you like, an eggshell structure within the rock, which will stand, as we know, for a considerable period. And that gives us time to advance through and take out all the excavation, and then we can cast inside it a concrete lining at our leisure.
The stability of the concrete walls would be severely tested soon after the channel opened, in a devastating trial by fire. Electrified fences, baited traps, pits and dart guns all protect the channel from rabid foxes and terrorist attack. Modern marvels will return. Now return to the channel on Modern Marvels. Putting a train tunnel through the English Channel involved more than, well, just putting a tunnel through the channel. A 31-mile passageway, 23 miles of it underwater, requires its own infrastructure, including cooling, pumping, and ventilation systems that make the whole operation efficient and safe.
This is actually W1 pump station, one of 3. all told. You've got 2 on the English side and 1 on the French side.
5 pumping stations like the service tunnel are responsible for keeping the underground pathways dry. Engineers planned for water to seep down from the channel at the rate of 150 liters per second, which sounds like a lot, but works out to a liter per kilometer. Minimal seepage is a good thing, relieving some of the stress created by the immense weight of the seabed and the channel. Pipes are everywhere in the channel complex. Pipes that keep it dry and pipes that keep it cool, carrying cold water through all the passageways.
If we didn't cool the tunnel, the friction of the trains moving through the air would cause the temperature to rise to about 30 to 50 degrees centigrade, which is somewhere in the region of about 120, 140 degrees Fahrenheit. This would mean that air conditioning of the through trains and the shuttles would be extremely expensive in fuel, and you'd get a circular argument of heat generated, air conditioning throwing out more heat, and therefore we have to cool it.
Cold water keeps the temperature in the channel a constant 50 degrees. The water in the pipes is chilled here at a cooling plant at the foot of Shakespeare Cliff, next to the original entry point to the tunnel worksite. When it's cold outside, a series of radiator-like fans are enough to keep the pipes cool. In warm weather, enormous chillers are used, 4 of them, each one loaded with 5 tons of refrigerant, the equivalent of 5,000 home freezers. The chillers are among the most powerful in Europe. Each one can reduce the temperature of 200 gallons of water by 6 degrees in a single second.
As you can see, it's very windy, about 15 miles an hour.
Ventilation of the channel is another vital issue. There has to be a way of getting fresh air into the passageways and of controlling smoke or toxic fumes in case of emergency. Huge ventilators housing gigantic fans, each one equipped with 34 blades, do just that, blowing a constant draft, 161 cubic meters of fresh air per second through shafts like this one in the service tunnel, which distributes the air to the other passageways. Much of the air stays in the service tunnel, which is pressurized to provide a safe haven during a fire. By maintaining higher air pressure in here, smoke or other contaminated air can't seep in from the outside. The tunnel floors, of course, had to be paved and lined with track, over 100 miles worth of state-of-the-art sensor-laden rail that doubles as a signaling system, shooting streams of digitized information to computers on board trains. Catenary lines were installed to deliver power to the trains. In normal use, the channel needs 160 megawatts of electricity, the same amount used by a city of 250,000. In May 1994, after centuries of talk and nearly a decade of construction, the Channel Tunnel was ready for traffic. A lavish banquet in the British crossover chamber marked the occasion. The channel was built with 3 kinds of trains in mind. A passenger train that could speed from Paris to London in 3 hours, and 2 shuttles, a covered one for cars and a larger lattice-framed one for heavy trucks. Both could cross the channel in 35 minutes. The shuttles were especially designed for the channel to make it easy for vehicles to get on, go through, and get off the trains. The wagons carrying trucks are the largest train cars ever built and boast the best speed-to-weight ratio of all time.
These trains were of a completely new type because of the need to have a very quick transit through the channel, and that led us to have trains running up to 160 kph and weighing up to 2,500 tons. Generally speaking, in the railway world, you have fast trains, which are light, or heavy trains, which are slow. And we have both here. That was the new fact.
Critics had warned that a channel train could become the world's longest crematorium, and fire was a major consideration in their design. The wagons are made from special alloys that can burn for 35 minutes, the length of a trip through the channel, without warping. Unfortunately, the various fire detection and alarm systems were put to the test less than 3 years after the channel opened. On November 18, 1996, a truck shuttle caught fire as it entered the channel at Calais. Authorities believe that a torch was tossed onto the train, starting the blaze. The flames quickly spread to a truck loaded with 20 tons of animal fat. The resulting inferno reached a temperature of 1,300 degrees and had passengers gasping on the train car floor. The shuttle tried to race through to the British side so that firemen could work in the open air, but wind generated by the speeding train spread the fire from wagon to wagon until 14 of the 28 cars were ablaze. Finally, the Euro shuttle came to a stop about 10 miles out of Calais.
By the time it was halted in the middle of the tunnel, most of the train was a raging inferno, and all the wagons were melted down just like huge dollops of metal, and they did have to be prized away from the line. The line was totally destroyed, and it was very, very lucky that nobody was killed. That's because they managed to get out of the train and into the service tunnel and away from the danger. The fire then began to eat into the main superstructure of the tunnel itself. Given another hour or two, if that fire hadn't been brought under control, maybe there would have been a collapse, which would have brought the whole thing down.
As a result of the near catastrophe, Eurotunnel has made key changes in its firefighting strategy. Instead of ramming through to daylight in a literal blaze, the plan now is to stop in the tunnel, let passengers escape to safety, and fight the fire with hoses and suppressants on board the train. The fire has certainly not deterred people from using the channel. 31 million people a year, 1,000 cars an hour, now cross the English Channel from below. Many of them make day trips from England to France to shop.
You can even buy Irish Guinness in France cheaper than you can buy it in England. That's the advantage. You can buy wine.
Pounds a bottle.
People will go from the UK across to France for a night out and then come back. I mean, that is just extraordinary. It wouldn't have happened, you know, it couldn't have happened 20 years ago.
Channel traffic is expected to double by 2010, and Eurotunnel has already submitted plans for a second channel tunnel, possibly for cars as well as trains, to be built in 2020. This despite the fact that it'll still be years, perhaps decades, before Eurotunnel investors see any profit on their historic venture. All earnings so far have gone to pay off the immense debt incurred in funding the $14 billion project. But numbers don't really tell the story of the Channel Tunnel, a story not so much of profit and loss as of incredible engineering and the irrepressible human desire to stretch across distances, overcome natural and cultural boundaries, extend the limits of technology, and find a cheaper bottle of wine.
Squids use ink to cloud the water and escape. We use it to draft our freedom. Some even use it for some freaky-looking tattoos. It's one of the most useful inventions of all time. 3,000 years in the making. Don't miss Ink on Modern Marvels. Tonight at 10 on the History Channel. Bolivia.
Railway world, you have fast trains, which are light, or heavy trains, which are slow. And we have both here. That was a new fact.
Critics had warned that a Channel train could become the world's longest crematorium, and fire was a major consideration in their design. The wagons are made from special alloys that can burn for 35 minutes, the length of a trip through the Channel, without warping. Unfortunately, the various fire detection and alarm systems were put to the test less than 3 years after the Channel opened. On November 18, 1996, a truck shuttle caught fire as it entered the Channel at Calais. Authorities believe that a torch was tossed onto the train, starting the blaze. The flames quickly spread to a truck loaded with 20 tons of animal fat. The resulting inferno reached a temperature of 1,300 degrees and had passengers gasping on the train car floor. The shuttle tried to race through to the British side so that firemen could work in the open air, but wind generated by the speeding train spread the fire from wagon to wagon until 14 of the 28 cars were ablaze. Finally, the Euro shuttle came to a stop about 10 miles out of Calais.
By the time it was halted in the middle of the tunnel, most of the train was a raging inferno, and all the wagons were melted down just like huge dollops of metal, and they did have to be prized away from the line. The line was totally destroyed, and it was very, very lucky that nobody was killed. That's because they managed to get out of the train and into the service tunnel and away from the danger. The fire then began to eat into the main superstructure of the tunnel itself. Given another hour or two, if that fire hadn't been brought under control, maybe there would have been a collapse, which would have brought the whole thing down.
As a result of the near catastrophe, Eurotunnel has made key changes in its firefighting strategy. Instead of ramming through to daylight in a literal blaze, the plan now is to stop in the tunnel, let passengers escape to safety, and fight the fire with hoses and suppressants on board the train. The fire has certainly not deterred people from using the channel. 31 million people a year, 1,000 cars an hour, now cross the English Channel from below. Many of them make day trips from England to France to shop.
You can even buy Irish Guinness in France cheaper than you can buy it in England. That's the advantage. You can buy wine.
Pounds a bottle.
People will go from the UK across to France for a night out and then come back. I mean, that is just extraordinary. It wouldn't have happened, you know, it couldn't have happened 20 years ago.
Channel traffic is expected to double by 2010, and Eurotunnel has already submitted plans for a second channel tunnel, possibly for cars as well as trains, to be built in 2020. This despite the fact that it'll still be years, perhaps decades, before Eurotunnel investors see any profit on their historic venture. All earnings so far have gone to pay off the immense debt incurred in funding the $14 billion project. But numbers don't really tell the story of the Channel Tunnel, a story not so much of profit and loss as of incredible engineering and the irrepressible human desire to stretch across distances, overcome natural and cultural boundaries, extend the limits of technology, and find a cheaper bottle of wine.
Squids use ink to cloud the water and escape. We use it to draft our freedom. Some even use it for some freaky-looking tattoos. It's one of the most useful inventions of all time. 3,000 years in the making. Don't miss Ink on Modern Marvels. Tonight at 10 on the History Channel.
Bolivia.